Welcome back, ladies and gentlemen. This is Chapter 8, Section 8-1. Okay, so I would say that Chapter 8 and Chapter 9 are kind of confusing. The other chapters, I would say, are pretty what we call algorithmic. An algorithm is just a step-by-step process for doing something, a computer algorithm, a math algorithm, or what have you. So the other chapters are kind of algorithmic. You just kind of plug in the formulas and you're good to go. Chapter 8 and Chapter 9 require quite a bit more thinking. However, the flip side of that coin is Chapter 8 and Chapter 9 are, I believe, the most interesting chapters and really the point of this entire class. So let me see if I can give you an overview. Chapter 8 and Chapter 9 both deal with a concept that is referred to as hypothesis testing. So let's take a quick look here at the author's discussion. How much better is better? Okay. And here's a scenario. The school superintendent reads an article. Overall mean score for the SAT is 910. He tests his kids and they get 960. Now, can you see how that would be a very, very common situation? You have an average overall mean of a population is some number. You look at your kids or you look at your whatever it happens to be, and it's more or it's less, and you say, gosh, seems like mine is more than the others. So you might think at first glance that, well, 960 is better than 910, therefore on average, the students in this school district did better, okay? You might think that because 960 is more than 910. But what you need to remember is that we know from our previous studies is that the means of samples, so you take a bunch of samples from a population, those means themselves, the X bars themselves, those are actually a random variable, and they can vary about the mean. We know from the central limit theorem that there's a mean of the X bars and there's a standard deviation of the X bars. So you don't have any way of knowing if this sample that you chose from your superintendent school, maybe it just by random chance happens to be higher than the population in general. Maybe if you went out there and you picked another sample of those kids, maybe they would be lower than the average from the population. So you don't know just because of the raw scores, just because the number is higher than the other. That is not a scientifically sound conclusion to say that it is your mean is better than the other mean. Okay, so the question always arises: is there a real difference in the means, or is the difference simply due to chance, i.e., sampling error? So remember, sampling error just means that we're taking a sample, so we're not measuring the entire population. So it's very easy to just by random chance get a sample that is different from the population. So in this chapter, Chapter 8, and then in Chapter 9, we're going to learn how to answer that question. A scientific way of trying to decide, is there a difference? And the words we normally use is we say, is there a statistically significant difference? Now, I want to urge you to look about in your daily life. It is absolutely impossible for you to go a week without seeing something in the news or on the internet, on TV or what have you, where people are not talking about this, but 99% of the time they get it wrong. No politics, okay? No politics. But for example, there has been a lot of discussions at the daily White House briefing talking about these wild and crazy ideas that the president has about the various treatments that are possible. Okay, he's mentioned such things as shining lights inside of people. He's mentioned such things as certain malarial drugs. So how would you answer that question? How do they decide whether or not a particular medication has any effect whatsoever? We do it with hypothesis testing. We test people and we gather the data and we do a statistical test. So what's really great about this course is that when you finish this course, you're going to be able to have such critical thinking that you can answer those types of questions. For example, does this malarial drug really fight the COVID virus? Does this particular toothpaste do better than a different toothpaste in fighting cavities? All of those kinds of questions will be able, you will be able to analyze using this class. Okay, so here he goes into the introduction. He talks about the kinds of questions that researchers are looking into. You might want to know, is there any evidence of global warming? A doctor may want to know whether this new medication will lower a person's blood pressure, or will this medication cure COVID-19? Educator might want to know about a new teaching technique. All kinds of things. Whenever you are comparing things, you must use a scientific method in order to be credible. You have to do this hypothesis testing. Is there a statistically significant difference between the two ways of doing things? All right, so I'm going to let you read that, but by golly, you better read it, and you better be thinking about this all during the week, because these two chapters are very difficult in my view. Okay, so then he talks here about the different ways of doing it, so-called traditional method, so-called p-value method, and the confidence interval. Okay, so we're going to talk about these, and you'll see what I'm talking about here very shortly. However, before I get actually started on Chapter 8, I want to compare and contrast and interrelate Chapter 8 and Chapter 9. In my experience, people get this so confused, and one of the reasons is because they seem so similar. Okay, so let's take a look here at the table of contents just to get an overview here. In Chapter 8, we're talking about hypothesis testing. Chapter 9, we're talking about hypothesis testing, even though he doesn't use the words hypothesis testing in the chapter. The thing that causes the confusion, I think, for a lot of folks, and this, I've seen this so many times, is that in Chapter 8, we're talking about, comparing a mean, comparing a proportion, and so forth. And then in Chapter 9, we're doing the same thing. We're comparing two means. We're comparing two proportions, and so forth. So it seems very, very similar. So what in the world is the difference between Chapter 8 and Chapter 9? And the formulas are very similar as well. At least the names of the formulas are, at least. And that can make you crazy. So let me try to save your sanity here. And I recommend write this down in your notes. Chapter 8, we are comparing a sample to a population. So that's the example the author used, where you take a sample of kids from one high school, and you can take that sample and you compare them to the entire population of all the high school students in the country. So Chapter 8, I compare a sample to a population. Chapter 9, what I'm doing is I'm taking two samples and I'm comparing the two samples. Okay, so do you see the difference? In Chapter 9, I am comparing sample to sample. In Chapter 8, I'm comparing sample to the population. So as we go along, my strong suggestion is find an example that makes sense to you, that you're interested in, and have it absolutely memorized so you can always come back to it and you'll know, am I doing Chapter 8 type analysis, or am I doing a Chapter 9 type analysis? Have an example that is significant to you, and if possible, kind of the same idea, a medical example, a business example, a science example, whatever is of interest to you. Try to have an example for 8 and 9 that are, kind of the same topic, but that clearly differentiate themselves from each other, and that will help you decide when you're doing a test, which techniques am I using, Chapter 8 or am I using Chapter 9? Okay, so without further ado, let's get started here. So section, let's see here. Let's go back. All right, so I like to always do a little bit of an overview here. We're in Chapter 8, so this is comparing a sample to a population. the first part here, he just gives you all the steps in the hypothesis testing. How do we do it? What's the typical scenario, the typical algorithm, okay? Now, 8.2 is a so-called z-test, and 8.3 is a so-called t-test. So we'll see here there's a distinction. There's two different ways of doing it. Kind of similar to what we did before when we did the confidence intervals. If we knew, in the confidence intervals, if we knew the population standard deviation, we would use the z-test. If we didn't, we would use the t-test. It's the same concept in chapter 8 now. We're talking about these the z-test for a mean. We use the z-test if we know sigma. That's the population standard deviation. We use the t-test if we do not know the standard deviation for the population. All right, so now we got a z-test for a proportion, and just like before, we don't have to worry about knowing the sigma for the population, because we're going to be using proportions. That's basically a binomial distribution. A binomial distribution is very easy to compute the standard deviation. The standard deviation is the square root of NPQ, so we don't have that problem of not knowing it. Okay, 8.5, chi-squared test for variance or standard deviation. Turns out that we can do many times we want to know, is there a significant difference between the chi-squareds between our sample compared to our population? And then we got some additional topics. Maybe we'll cover that, maybe we won't. Okay, so in the back of your mind, and I want this to be just a Pavlovian response. I hope you know what Pavlovian means. If you don't, Google it. If there's I want you to have this Pavlovian response. Whenever we're talking about hypothesis testing, the critical question is there a statistically significant difference? That's the question. There's always going to be a difference, right? I mean, you wouldn't even do the test if there wasn't some difference, right? I mean, it doesn't make any sense. Why would you even do the test? The question is there or is there not a statistically significant difference? So that's what chapter 8 is going to be about. We're going to get to that in the very next recording. So this is the end of recording number 1.